My name is Vlad Galu. I'm with the Inmarsat core network engineering team. My particular duties involve coordinating the software engineering efforts. As you're about to, we have some homegrown software that we use to address some of the issues of satellite conditions. I'm going to talk about BGAN, which is our broadband global area network. This picture will show you the coverage, approximate coverage that our satellites provide, the Inmarsat 4 satellites. We cover pretty much everything except for the poles. And we provide data voice services to a number of customers. You could call them high profile. Probably the biggest one is the US Department of Defense. Most of the military deployed in Iraq, Afghanistan, wherever they don't have any kind of other kinds of access to the internet, they use our network. If you watch BBC live coverage from these war zones as well as others, those reporters will use Inmarsat's BGAN. We also have customers from the oil and gas industry, people working on oil tanks, on oil rigs, as well as they have different uses for our system as well. They have metered gas pumps, and they send remote telemetry data to some terrestrial data center. As I've already mentioned, boats. If you're on a boat in the middle of the Atlantic or the Pacific, you're not going to have any other way of going online unless you use our service. Also, organizations such as the Red Cross, who are deployed on short notice to other places with critical issues, take our devices along with them. I haven't covered this in the slides, but our typical satellite modem is not really bigger than the laptop you're using right now. Some of them are smaller, some of them are large, slightly larger, but they all fit in a backpack. So mobility is the keyword. You could go on a trek somewhere in the open and just carry the laptop and the satellite modem. So we do cover mostly everything from a geographical perspective, but we have an nemesis, which is latency. The typical physical latency, if you will, to geosynchronous orbit is about 500 milliseconds, and we have a protocol overhead of about 300 milliseconds. Now, Inmarsat services are differentiated in what we call a background and the streaming mode. The background mode is your average service that is billed by the amount of data you consume and is a completely best effort service. And the streaming mode has a guaranteed pipe. Due to some design decision that was taken 10, 12 years ago, there's some additional queuing in the RAN, which we will soon get rid of in our next generation network. So BGAN was deployed in 2005, well before the worldwide adoption of 3G networks. Back then, you had operating systems like Windows XP, even older than that, Windows 2000. The TCP stacks in those systems were never optimized for long and slow links. Basically, TCP, if you have a dropped packet, would assume there's a congestion on the network, but in our case, a dropped packet won't necessarily mean we have a congestion. A dropped packet could occur from ground RF interference or clouds or a storm and whatnot. In 2005, both the clients and the servers at the end, the two endpoints of a TCP connection had very small windows. Both the advertised window of the receiver and the congestion window of the sender were really small. So let's say you were to upload a 10 meg file or a 100 meg file over the satellite link. Because of the RTT, and the particular implementation of the stacks at the time, if you were to drop packets, let's say 1% of the time every 30 seconds or so, then your congestion window would drop. In some implementations, such as Neurino, it would drop to half of the current value. Others would just drop to 1 MSS and start over with a slow start, with a congestion avoidance phase, which essentially increases the congestion window in a linear fashion rather than exponential fashion. Also, if you were to send 10 segments and the endpoint reported, hey, I dropped the second segment, you would have to resend that and all subsequent segments because those systems didn't support selective acknowledgements. Also, with slow start, if you navigate the web, most small pictures and resources would fit in a couple of window sizes, which means that instead of the server simply sending them to the client in a burst and only then waiting for acknowledgement, it would go through the same very, very slow start. So even before this system was deployed, we had to come up with a solution that would alleviate the latency issues. And it is called the TCP PEP. It's not a very imaginative name. PEP means Performance Enhancing Proxy. What it actually does, it splits the TCP connections at the network level. The most significant change is that it uses TCP Vegas, which is a delay-based congestion control algorithm. So instead of using the number of acknowledged bytes to determine the congestion window size, it will continuously probe the end-to-end latency and use that to factor in this congestion window size increase and decrease. It also ramps up the congestion window size for both ends as well as the receive window size. We spoof that both in the network and on the client side. So that if you were to log on Facebook from your satellite connection, believe it or not, this is a very common use, you would just send most of it before waiting for the first stack. We also do SAC. As I mentioned earlier, this was a huge penalty to most connections. We also implemented TCP timestamps to help us with reordering. That almost never occurs on the satellite side because of the way our air interface is designed, but rather on the terrestrial side sometimes. We also added transparent payload compression for TCP packets. So this is a blind payload compressor using the LZ algorithm. In 2005, the web was nowhere as rich as it is now. It was still mostly text-based, and servers were still sending out uncompressed, ungzipped pages. All these capabilities are negotiated by the endpoints, which in this case would be a piece of software the client installs on his machine, and the network side machine we've built using the TCP options. We can push as many TCP options we need because the SYN packets are really small. And if the customer doesn't install the client-side software, they would still benefit from the downstream acceleration, but they won't benefit from the upstream acceleration for uploads. I'll have to mention the fact that until recently, Inmarsat hasn't sold these services directly to end users, but through a network of partners. In the mobile world, we call them MVNOs. All these end customers are then assigned to a particular APN, and using that information from the GGSN, we further route their traffic. The convention was that they would provide layer 7 acceleration as a differentiating factor because some of them had certain types of customers, some of them had other types. So for instance, you would have resellers who focus on the maritime market, and In the maritime market, you would typically have a ship with 30 to 40 people, and they would all use corporate email. They would receive the same email. Some people in management send out a document that is addressed to everyone on board. So there are optimization solutions that terrestrial people are very eager to dismiss. They're called WAN optimization products, and they focus on data reduction. They work a bit like BitTorrent. They split the traffic in chunks. By the way, this is completely protocol agnostic. So if you send out an email containing a large attachment, all that traffic will be split in, let's say, 8K chunks, and a checksum will be computed for each chunk. And then the two endpoints will say, hey, do you have the chunk with this checksum? If you do, I won't send it to you, and the files will be basically reassembled at the remote end. This has the extreme advantage that it works as with any protocol. So if you are to receive that file through, to download it over HTTP, if you download it over an unencrypted IMAP, the cache will still be effective. So this was in 2005. Oh, sorry. I have to mention, to say a few words about how we've integrated this. The UT is what we name, the name we use for the satellite modem, and the T is the terminal equipment, in this case, the user's laptop. Both of these, as you see in the diagram, the red traffic is the traffic we optimize using our TCP PEP. So it goes optimized up to the node that says GN PEP, and then from there to the GGSN out into the internet, it's normal TCP. On the client side, we stick between the Ethernet layer and the OS layer. Remember, we are still talking about legacy systems. We consider them legacy in 2012. So this is your typical Linux or Windows XP of 10-ish years ago. The application would speak to the host TCP stack, that speaks Reno or a dialect of that will then plug into our own stack, and we would replace Reno with Vegas over the air. On the network side, we had some challenges in deploying this box. Between the RAN and the SGSN on the IU interface, it was quite expensive to do so for two reasons. First off, the hardware to do it we required ATM cards. Those were quite expensive, and software-wise, that particular loop would see both circuit switch and packet switch traffic. So there was a lot of traffic we didn't really care for, the voice traffic that we would have had to still parse to some extent. On the GI, because of the way Inmarsat does business, we have a number of dedicated lines for tunnels established with all our resellers. So deploying there would have required breaking the IPsec tunnels, which was not something we wanted or could do. There was an idea at the time to simply loop the traffic out of the GGSN and back in while going through this optimization box, but since we have a few tens of MVNOs that we work with, and we have 2 GGSNs in every ground station, the operational overhead would have been too large to cope with. Every time you needed to change something, in both GGSNs in three sites. It's really easy to lose track of what you're doing. What we did instead was to deploy the accelerator on the GN segment between the SGSN and the GGSN. This had a number of benefits. Traffic is in the clear. We don't have to toy with IPsec at all. And it also gives us access to the GPRS header information. So we have the exact idea of the QoS. The user has pretty much everything. Also, as I'm about to mention later, all these MVNOs have been in love with RFC 1918. We have bashed it earlier. I can totally see why. So essentially, we have overlapping IP address spaces in use in the system, and the GPRS information allows us to make the distinction between 10.0.0.2 in one MVNO's network and the 10.0.0.2 in another MVNO's network. Moving on to today's requirements, we have witnessed a slow adoption of newer operating systems. On an oil rig or on a boat, or if you have a ruggedized laptop, you can't just upgrade your operating system. Some things might stop working. But as I've said, customers have slowly started drifting towards new stacks. The CTCP stack in Windows 7 and recent Windows Server versions is much better at recovering from packet loss. It's still not delay-based, but it's much less conservative in dropping the congestion window size. Linux from 2.6 to 0.18, I believe, uses Cubic, which is delay-based, and it's a lot better at handling loss on the server side. And you have Westwood Plus, which seems to be a preferred dialect by lots of vendors. Also, there are some people from the CDN industry in the room. They all say, hey, increase your congestion window on your server. So that would essentially mean that you rely on the receiver window size to control the flow of information. And most popular websites have already done that. Most of our traffic, I would probably say from 2/3 to about 3/4 of it is web. So this is where customers hurt the most. Pages slowly loading. The content is a lot richer. Back in 2005, there were not as many ads, not as many third-party scripts, not as many pictures. If you go on Facebook and you haven't checked your friends' walls for, let's say, a couple of days, you'll have a flood of dogs, cats, ants, food, whatever. What we've seen is that layer 7 acceleration tools have not been widely adopted by our resellers. Some of them are in the business of reselling hardware, so they make a slight they have a slight profit margin on that, so they were not exceptionally compelled to invest time and money into this. Also, recently, Inmarsat has purchased Stratus Global, which used to be our largest reseller. So all of a sudden, we have to handle the whole end-user relationship. We have to cater to their needs, to see what they want. This has all been opaque to us until now. The point is, we need to address that. We've run some profiling tests, and on most websites our users go to, it's not the pictures that take the most of time to load, but rather the third-party JS and CSS resources that are usually hosted outside the domain of the website you visit. So there are a number of things we can do about that. As I said, these might seem silly if you're a terrestrial operator, but for us, throwing money at a problem is not really, for most people it is expensive, but for us it's even more so. It takes $1.5 billion just to build 3 satellites, probably just as much as that to put them into orbit. And if you factor in other things as terrestrial costs, you end up with a really nice figure. So we are trying to deal with what we have available. To develop a layer 7 acceleration solution now would be overkill for us. It would just take too much time. So we're looking at a number of them. We're trying to please as many people, to shoot as many flies as we can. As I said, some of them address the remote office type of customer, which ships and oil rigs are, but most of our users are lone rangers. Your typical National Geographic reporter goes out in the field, takes a picture of a nice flower or animal, sends it back to the back office. So on layer 7, there's still a lot of room for improvement. We can look at HTTP request coalescing, which is essentially this. You send the first get to the web server, and instead of fetching the main HTML body and then resending GET requests for all the objects in the page, a third-party solution would prefetch the page for you, inline all text content like JavaScript or CSS, compress the pictures, and then send the reply back as a single object. Given our RTT, this would vastly improve the page load times. Lossy compression is something some of these vendors can tweak. They can store per user settings, and each user can visit a certain URL and set its own compression level. Some of them would tolerate pixelated pictures, provided they load fast enough and the browsing experience is smooth. Some of them won't, but the point is we are trying to find a solution that would give them the choice. Also, if you trim the text, has anyone looked at the source of any website that they usually visit? There's a lot of white space, a lot of new line that can be easily compressed. So all these solutions optimize the text content and deliver you a blob of text, no white space, no new lines, nothing. It should look the same in the browser because they're not changing much. There's also one point that is still bugging us. You have ads, and they're typically hosted outside the website you are visiting. If we were to inline those and deliver them to the customer as part of the main web page, we would be essentially defeating NoScript, because most people have ad blocking add-ons in their browsers that work on a whitelist or blacklist or a graylist basis. So we would doing more harm than good with this. More challenges. I've already mentioned the overlap. These off-the-shelf boxes do not normally support GPRS. None of them have this capability. Some of them allow you to do certain things with radius in order to tell which customer is which, but most of them would do segregation on a VLAN basis or a MPLS tag basis. So it's all about making it possible for that box to intercept the traffic and optimize it in a segregated fashion. Essentially, we would have to build a box. That's one option we are considering, to do NAT based on the GPRS header information and the IP header information, and to map those pairs, which are unique, to another unique IP address, send the packet towards this third-party box that would send it towards the terrestrial side, where we would DNAT it, essentially. So we would have to build a box that maintains a two-way mapping between the GPRS domain and the IP domain. There are some other challenges related to the way we place these boxes. If we deploy them in our ground stations, we would need to have at least one or two for each ground station, which would be quite expensive. If we deploy it in the GGSN in a looped fashion, it's the same thing as before. Currently, our GGSN cannot do it. We were told by our GGSN provider that this feature will be supported in the next software release, but in this environment, you can't really ask for a software upgrade just for this, because there are lots of customers involved. And I've already mentioned the natting possibility, which would essentially be looping all the traffic from our current accelerator to this third-party layer 7 accelerator and then back and sending it through. Starting next year, we'll slowly roll out the new Inmarsat service, which is a much higher speed service working in K-band, we'll be achieving speeds up to 50 megabits per second on the downstream side and 5 megabits per second on the upstream side. Also, the latency is going to be a lot lower. Our engineers have redeveloped the air interface for these devices and taken most of the protocol, layer 2 protocol overhead. So we should see latencies, sub-second latencies, somewhere around 600 milliseconds or so. The downside regarding the terminals is that they'll be quite large. So we'll go from the BGAN terminals, which are about this size, to this size. You obviously won't be able to shove those into your backpack. Some of them will be even larger than that. And they will require much better pointing accuracy because they'll be VSAT terminals. So all of them will have a built-in GPS, compass, and gyroscope. They will all need to point directly at the satellite at all times. Even a tenth of a degree variation would essentially break the link. Although I've mentioned that the layer 3 will become less and less of a concern, we couldn't help ourselves and developed a layer 3 acceleration feature into these Global Express devices that could be turned on or off by the user, that will use layer 2 information in real time to react. So instead of having TCP probing the pipe to try determining the latency and the available bandwidth, it will get that from the device it's working on top of and react immediately. That would shave off some cycles as well. And this network will be IPv6 ready from day one. Right now our network BGAN supports IPv6, but none of the MVNOs we work with use it. Another challenge we have is once let's say we find the perfect solution for our customers as far as layer 7 acceleration goes, we will still have to find a way to use it with both networks. So that's mainly a cost issue, but we'll figure something out. I think I pretty much covered everything. If there are any other questions, we're running short on time. We could take these afterwards, or however you prefer.
Idea in terms of your NAT before your WAN accelerator, basically, might be easier. Can you not just 802.1q VLAN tag them for each of your customers, and the WAN accelerators might see those tags? Can't you tag each one of the customers at 802.1q before your web accelerators? Then you might not need to do your NAT.
Yeah,
they might support
VLAN tagging either NAT or VLAN tagging would just provide the means for these third-party acceleration boxes to distinguish between two different customers sharing an IP address. But once the traffic is looped back into our network, it will be denatted. So the reverse mapping will be applied to that traffic, and it will go to towards the internet in a purely transparent fashion as far as the user is concerned.
Yeah, sure. Okay, sure. Thanks.
Hi, David Friedman from Claret. Do you have any idea of how many of your customers run VPNs on top of your service, and this would be pretty much useless for them?
There's quite a sizable amount of them, particularly the military ones. They don't want us snooping into our traffic at all. So we simply bypass that traffic. All traffic we can't understand, we simply forward. So it's really their concern how they address the latency issues on an end-to-end basis. So to answer your question, we don't do anything for the customers using VPNs.
Okay, thank you.
There's another one. I think
okay, one more.
I didn't hear a lot about IP6 in that.
Sorry?
I didn't hear a lot about IPv6 in
No, I've mentioned it in pertaining to the GX network. So I've mentioned that currently we do support IPv6, but none of the MVNOs we work with have deployed it.
Okay, talking about MVNOs, do you do L2TP handover, where the addressing and the acceleration and anything is not your concern, it's all handled by your MVNO or supplier?
No, we see their traffic packed in GPRS, in GTP headers. We have a system, a whitelist system based on APN or IMSIs, so that we can say, okay, for this IMSI or for this APN, just forward the traffic, don't take it through the layer 3 accelerator. Some of them have specifically asked that we do that, so we do that.
Okay,
Okay,
thank
I
you,
think that's
Vlad.
all.